Assalamu alaikum wa rahmatullahi wa barakatuh. Thank you, bro, for giving us this opportunity to present this assignment. The title of the assignment is Modeling Network Queuing Algorithm. My name is Sharmaka Adam, and my groupmate is Mustafa Yusuf. In the introduction, traffic shaping is a computer network optimization technique that improves bandwidth management, latency reduction, datagram prioritization based on the necessity. The two most basic traffic shaping strategy are the leaky packet and the token packet algorithm. The average drop rate of the leaky packet method facilitates packet flow, and basically it contains packets that exceed its buffer limit. So if the buffer limit is exceeded, the packet is simply dropping. The token packet in a token packet is fixed. When a packet commits, the packet is searching for available token. And if one is found, the packet captures the token and transmits it. If not, the packet is stored at the buffer. The two traffic shaping algorithms that we have investigated and explained in the book by using ONNET++ and mathematical principles based on leaky packet and a token packet algorithm. So the procedure, the leaky packet and basically token packet algorithm, which are the two most often used traffic shaping models, are detailed below. Leaky packet algorithm steps. Step number 1, at each tick of clock, add a counter with the value of n to the buffer. And step number 2, send the packet to the network and subtract the counter value by the size of the packet. If the value of n is larger than the arriving packet size, then step number 3, repeat the preceding step until the packet size is smaller than n. Step number 4, restart step 1 after resetting the counter value. Okay, this is the leaky packet algorithm figure, which is the right side. There is a packet, there's a droplet is packet, then the packet is leaking, so water droplet is flowing at constant rate since it is leaking. And the right side figure is a computer host. There is a packet flow, which are unregulated way. So we have packet holding the packets which are coming from the computer host, and interface containing leaky packet. So this packet contains an interface, a leaky packet, and then packets are gone through the packet in a regulated packet flow. Okay, token packet algorithm steps. Step number 1, at every t interval of a time, a token is added. Step number 2, the token packet can only carry one head token at a time. The token hits the packet while it's already full, it will be rejected because it was already full. Step number 3, when a packet of n bytes is received, it takes n tokens and sends it to the network. Then step number 4, if there are less than n token available, the remaining packets will be held in the buffer until enough tokens have been acquired. Okay, this is this token packet algorithm diagram. This photo, which is this diagram, which is at the left side, is showing us there is a host computer. It is actually showing a packet holding 3 tokens with a 5 waiting packet to be transmitted. So for a packet to be transmitted, it must capture and destroy 1 token, and at a clock rate of a time change or interval of a time. Then the right side figure, which is a token packet algorithm after, that other one was before, and this is after. The 3 of the 5 packets have gotten through, but the other 2 are stuck and waiting 2 more tokens to be generation. That's all for me, and I would like to pass to Mustafiz to present the rest. Thank you.
Assalamu alaikum, Professor. This is Mustafiz. Thank you for the opportunity that you've given to us, and thank you, Sharma, for finishing your part. Let's start with the data and result analysis. Flowchart of leaky bucket algorithm implementation. Here, arrival of the packets at time t, and then it goes to the next state, which is auxiliary variable x dash equals to value of leaky bucket counter x, which is subtracted from t last confirmation time. And then it will go to the condition check auxiliary, whether the auxiliary variable is x dash is less than 0 or not. If it is yes, then auxiliary variable x dash will be equals to 0. And if it is not, then it will go to the further condition check, which is auxiliary variable x dash, whether it's going to be greater than tolerance or not. If it is yes, then the non-conforming packet. And if it is not, then the value of leaky bucket counter x equals to auxiliary variable x plus 1. And last confirmation time equals to t conforming packet. Let's start with the state transition diagram of leaky bucket algorithm. Here, the packets arrives in arrival. Then, if the bucket is full, then the packet will be dropped over here, and then it goes to the idle default stage. And if from the arrival, if it sees that the bucket is empty or has space, then it will the packet will be served, and then it goes to the idle default stage, and it follows the same iteration. Then simulation of leaky bucket algorithm using Omnet++. This module contains a drop trail queue and the packet server. The queue capacity and the processing time of the server can be used to parameterize the leaky bucket algorithm. In this simulation, we made the network, which is ID1, and then we try to make the leaky bucket, which is ID2, then passive packet sink, which is ID3, and active packet source, which is ID4. Here, the packets are produced by the active packet source, and then the packet source pushes the packets into a leaky bucket module, which pushes them into a passive packet sink. And the leaky bucket is here actually configured with a processing time of 1 second and a packet capacity of 1. Inside this bucket, leaky bucket, there are a queue and a server. Initially, the queue actually contains 0 packet, and once the packet comes from active source and pushes 1, pops 1, drop 0, and it goes to the server for further processing, and then it goes to the passive packet sink. Then the flowchart of token bucket algorithm implementation. Here, the packet arrives at packet arrival, and then the packet is stored in buffer at first in, first out FIFO manner. Then it goes to the to check whether the token is available or not. On the other hand, token refill at a fixed rate, and it goes to token buffer and goes to whether the token is available or not. Once the token is available, packet transmits at fixed rate. If there is no token is not available, then it waits until tokens are available. Then state transition diagram of token bucket algorithm. If token is available, is not available, it generates token over here by the token generation and sends the token to the token buffer. On the other side, actually packet arrives in the packet arrival, and then it checks the token buffer whether the token is available or not to facilitate the packet over here. If token is available in the token buffer, packet is being facilitated, and it goes to the network. On the other side, the packet is stored at FIFO manner, fast in, fast out manner in the buffer. Simulation of token bucket algorithm using Omnet++. In this simulation, the module, actually this module contains drop tail queue and a token-based server. The queue capacity and token consumption of the token-based server can be used actually to parameterize the token bucket algorithm. The module uses an external token generator for the token-based server. Actually, this is the token generator over here. In the simulation, packets produced periodically by the active packet source, which is this one, and the packets are pushed into the token bucket, then which pushes to the packet to passive packet sync. And the external token generator is time-based token generator, which actually generates the token periodically into the token bucket module. Inside this bucket, actually, it contains one packet and it pushes one, pops one, and drops to 0, and it goes to the server for further processing. Conclusion. The flow of network traffic really uniform, and it is categorized by the period of burstiness. Two main network model queuing algorithms are leaky bucket and token bucket algorithms. Few key metrics should be analyzed in order to evaluate the network model performance, such as throughput, wait time, packet loss, and others. That's all from me. Thank you for the opportunity once again. Thank you, Professor.